Hi ladies, this is Mrs. Blaufuss here, and today we're going to look at lesson 8.2, and this lesson talks about graphing simple rational functions. So before we can start graphing a simple rational function, let's first define a rational function. So a rational function is a function in the form p of x over q of x equals f of x. And because we're dividing two rational functions, we have to define q of x because it's in the denominator, where q of x does not equal 0. And then secondly, we're going to define p of x and q of x so they're both polynomials. Now let's look at the graph of the parent function of a simple rational function. So you can see here that there are two asymptotes. The first one is a vertical asymptote, and that is when x equals 0. So if you think of what a vertical asymptote is, that's an x equals line. And in this case, it's just an imaginary line that goes along the y-axis. So anywhere on the y-axis is where x equals 0. And then the horizontal asymptote is when y is equal to 0. So we can see this horizontal asymptote here, the point where each of the branches of the graph approach, but they never actually touch. So let's look at this section of the graph. And in this branch of the graph right here, if we define our domain and range of just this branch, it would be that x is greater than 0 and y is greater than 0 because it never actually touches the x or y axes. And then if we were to define this branch, the domain and range, we would say y is greater than 0, y is less than 0, and x is less than 0, but it's never actually equal to 0. Both of these branches are part of our graph of rational functions. And so when we define our domain and range of a simple rational function, looking at especially this graph, the parent function, we're going to say that x is not equal to 0 and y is not equal to 0. So the domain can be anywhere except equal to 0. If x is greater than 0, then our graph lies on this branch of the hyperbola. And if x is less than 0, it lies on this branch of the hyperbola. So x cannot be equal to 0 and y cannot be equal to 0. That's the domain and range of this parent function of a simple rational function. So if we look at this key concept, it says any function of the form g of x equals a over x, where a is not equal to 0, has the same asymptotes, domain, and range as this parent function. The only time our domain and range is going to change is, and you'll see it when we have an h and a k value, which we'll look at briefly in a minute. So now let's look at the graph of this function in the form y equals a over x. So as you just read in the key concept, it says that any function in the form a over x where a does not equal 0 has the same asymptotes, domain, and range of this parent function, which means x is not equal to 0 and y is not equal to 0. So if we look at this, we can define our domain and range right away. We know that this is in the form a over x, and therefore it has the same domain and range as the parent function, y equals 1 over x. And that domain and range is that x does not equal 0 and the range y does not equal 0. So let's go ahead and sketch in our asymptotes of our graph y equals 4 over x, and then we'll choose a couple x values on either side of the vertical asymptote, and then we will look at our graph. So in the green, you can see our vertical and our horizontal asymptote to exclude the domain restriction and the range restriction. So our asymptotes are, our horizontal asymptote is our x-axis where y is equal to 0, and our vertical asymptote is our y-axis where x is equal to 0. Now we're going to choose a couple points on either side of the vertical asymptote. Those will be our x values, and then we'll plot our y coordinates as they depend on our x coordinates. So I chose -2 and -1 for the left side of my vertical asymptote, and I chose 1 and 2 for the right side of my vertical asymptote. And I have these coordinates, -2, -2, -1, -4, 1, 4, and 2, 2. Now I'm going to plot those. Once I plot these points, you can notice that I'm going to have 2 branches, and each branch should be a smooth curve. So they should be approaching your asymptotes, but they should never actually touch those. And you can sketch your graph in and draw the curve as smooth as you can so that it goes through each of your points and approaches the asymptotes but never actually touches. So let's compare this graph to the graph of y equals 1 over x. And if you notice from this graph, it just is a little bit further away from the x and the y axes. The domain and the range are still the same, but it is further away from the intersection of the asymptotes. So there are a lot of similarities, but the one difference is that it's not quite as close to the asymptotes as the graph y equals 1 over x. All right, now let's look at the next example. If you're following along in your note sheets, there's this key concept, and this key concept graphs translations of simple rational functions. And here is your expanded rational function form, y equals a over x minus h plus k. These h and k values, we've seen these before, where h is a horizontal shift and k is a vertical shift. So you've seen that in a lot of different examples, including graphing parabolas, quadratic functions, graphing absolute value functions. You've seen it in vertex form. So you've seen these h and k values in many different places, and now we're looking at them in rational functions where we're looking at the hyperbola of the graph. But h has always stood for horizontal shift and k has always stood for vertical shift, and that's the same here. So when we graph this function, we're first going to draw the asymptotes, x equals h and y equals k, and then we're going to plot the points to the left and to the right of the vertical asymptote. Then we can draw in the branches of the hyperbola so that they pass through the plotted points and they approach the asymptotes. But remember, they never actually reach the asymptotes because those asymptotes are going to be restricted from our domain and range. Now, a simpler way to do this is to make a table and use points of the simple rational function y equals a over x. So just like we graphed the simple part of a exponential function and the simple part of a log function and then shifted it, that's how I recommend doing this because h again stands for the horizontal shift and k stands for the vertical shift. And this is a simpler algebraic equation to compute for various x and y values, and then you can shift x values horizontally and the y values vertically. So I would first graph this. And then we can shift. H units horizontally and shift k units vertically. Remember in your form you have in the denominator x minus h, that's the formula. So if it's x minus 3, your h value is positive 3, which means you'll move to the right 3 units. So let's look at an example here. We're graphing the rational function y equals a over x minus h plus k. In this case, the rational function is y equals -6 divided by x plus 3 plus 2. So first, let's define our h and our k values. So x plus 3 means h is -3. The whole function plus 2 means that k is positive 2. Okay, so that's our first step. And then from there, we're going to plot we're going to draw in our vertical and horizontal asymptote. So our horizontal asymptote is k equals 2. Okay, that's when y is equal to 2. And our vertical asymptote is when h is negative 3. That's when x is negative 3. Now I'm going to make a table and I'm going to graph, or I'm going to make a table for some points where y equals negative 6 over s. I'm going to do that first, and then I'm going to shift. So here are the x values that I've chosen. And again, I'm just first graphing this y equals negative 6 over x function. So if I choose negative 2, negative 1, 1, and 2 for this function, I'm going to now plug that into y equals negative 6 over x. And my values are y equals 3, y equals 6, y equals negative 6, and y equals negative 3. Okay, these are the points for the simple form y equals negative 6 over x. Now I have to shift my graph. So I have to shift it negative 3 units on the horizontal axis, which is 3 units to the left, and 2 units up. So 2 units on the vertical axis, which is 2 units up. So for each one of these, I'm going to subtract 3 from my x values. Because I'm moving it 3 units to the left. So my new x values are negative 5, negative 4, negative 2, and negative 1. And I don't have to plug them back into my equation because I'm just shifting horizontally. And now I'm going to shift my vertical. So that means I'm adding 2 points to adding 2 units to every y coordinate. That will be the vertical shift. So my new y coordinates are 5, 8, negative 4, and negative 1. Now I can go ahead and plot these. These points are to the left of my asymptote. And these points are to the right of my asymptote. So now I'm going to go ahead and plot those on my coordinate plane. Once I have my points plotted, I'm going to draw a nice smooth curve that goes through my points, approaches my asymptotes, but does not actually touch them. And if you notice, and this will always happen, your 2 branches on your hyperbola will be kitty corner of the plane formed by the intersection of your asymptotes. So if you look at these green asymptotes here, here's the intersection. If your first one is in this first or the second quadrant, so this is quadrant 2 actually, then your second branch will be in the kitty corner quadrant. So in this example, it's in the 4th quadrant. So it's always going to be kitty corner of the intersection of your asymptotes. And the last style of rational function that we have is where we have an x in the numerator and an x in the denominator. So these are still both rational functions, but we have an x in both the numerator and the denominator. Oh, you know what? We need to go back in the last example and state our domain and our range, because since we shifted the graph up and to the left, we have a new domain and range. So in this example, and your domain and range is always restricted by your asymptotes. So in this example, the asymptotes are the h equals negative 3 and k equals 2. So this graph, x equals negative 3, that's our vertical asymptote. So that is the one x value that's restricted from our domain. So in this example, the domain is not equal to h, which means x does not equal negative 3. So that's your domain. And your range is never going to be equal to your k value because that's your horizontal asymptote. So in this example, y does not equal 2. That's your range. It may help just to write that right away so you don't forget like I just did. So as soon as you know your h and your k values, write your domain and write your range. So let's do that right away with this example. So we're going to graph the rational function in the form y equals ax plus b over cx plus d. So this is our form that we're going to use. And our horizontal asymptote, our y, is going to be equal to a over c. So in this example, our a value is equal to 4. And our c value is equal to 1. So in this example, our horizontal asymptote is 4. It's 4 over 1, which is 4. So go ahead and draw in that horizontal asymptote. And our vertical asymptote, our domain restriction, is going to be whenever this is equal to 0. So the denominator cannot equal 0, therefore we are going to restrict x minus 1 equals 0 from the domain. So in order to restrict x minus 1 from the domain, we need to figure out what x is because our domain defines our x values. So you're going to solve for the domain is equal to 0. So in this case, x minus 1 is equals to 0 cannot be in the domain. So x equals 1 is restricted from the domain. Okay, so anytime it's in this form, you're going to solve for the denominator. You don't really care about the numerator because the numerator can be anything, but you're going to solve for the denominator because the denominator can never be 0. Okay, so our domain restriction, so our vertical asymptote is x equals 1. And this is our horizontal asymptote. Okay, so now let's go ahead and draw in our vertical asymptote. So again, this will be restricted from our domain. So our graph will never actually touch the line x equals 1 or the line y equals 4. So now we can go ahead and plot a couple points. We're going to choose some points to the left of the vertical asymptote and to the right of the vertical asymptote. -1 and 0 are to the left of my asymptote, and 2 and 3 are to the right of my asymptote. So make sure you pick a couple on each side of your vertical asymptote. So here are my coordinates for y equals 4x minus 2 divided by x minus 1. Again, avoiding my x equals positive 1 because that is my vertical asymptote. So I'm going to go ahead and plot these points, and I should see them on kitty corner quadrants of the intersection of my asymptotes. And then I'm going to go ahead and sketch in my branches of my hyperbola. That's the name of this graph that has 2 different branches. And again, draw nice smooth curves. You're not connecting the dots, and they should approach the asymptotes but never actually reach them. So if you're following along on your note sheets, there are 2 more examples, number 2 and number 3. I want you to try these on your own And actually, you know what? We didn't actually state our domain and range. We said we were going to, but we didn't. So let's actually state our domain and state our range. So our domain is any values that are not equal to +1, and our range are any y values that are not equal to 4. Again, your h in your case, or in this case, your vertical and horizontal asymptotes are the restrictions for your domain and range, because those are the only two values for x and y that they are never going to actually touch. They will approach but never actually reach your asymptotes. So in these next two examples, pause the video while you work, and you can unpause for the solution. It may be helpful to start with your domain and range. So define your h and your k, and define your a and your c, so that you can define your asymptotes and then state your domain and range, and then you can go ahead and plot your points. So pause the video now and go ahead and work, and you can unpause for the solution. So let's start just by defining our h and our k. So our h is 1. Nope, actually our h is 2 and our k is 1. So that means our vertical asymptote is x equals 2 and our horizontal asymptote is y equals 1. So we're going to go ahead and plot those. And then we're first going to graph coordinates for y equals 3 over x, and then we're going to shift them 2 units to the right and 1 unit up. I'm just going to pick a few points that are easy to plot, so 3s and 1s. And now before I actually graph these, I'm going to first add 2 units to my x and add 1 unit to my y. Then I'm going to plot my points and sketch in my hyperbola branches. And your final graph should look like this. Okay, now let's look at the next example, number 3, that you did on your own for the solution. Here I'm going to start by defining my a and my c values. In this case, a is -2 and c is 1. My horizontal asymptote is a divided by c, which is -2 divided by -1, and we get y equals -2. I'm sorry, I mean vertical asymptote is x equals -2, and horizontal asymptote is y equals +2. Your vertical asymptote, remember, you get by solving the denominator, -x minus 2 equals 0, and that is the number you are restricting from your domain. So your domain is all real numbers except when x is -2. Your range is all real numbers except when y is equal to 2. So now I'm going to make my x and my y table and pick a couple points to the left of the vertical asymptote and a couple points to the right of the vertical asymptote. Here are my values from the table. Now I'm going to plot them on my coordinate plane. Okay, and again, your hyperbola branches should be kitty corner of the intersection of your asymptotes. So in our domain, we have x is not equal to -2. In our range, y is not equal to +2. And so if you can see, like on the left, my top left branch of my hyperbola, that goes a little bit off the coordinate plane. That's okay. You can still estimate about where it should lie, so that your hyperbola branches are identical, just reflections of each other. So if you have any questions, please bring them to class and we can go over them next time I see you. Thank you.